Investigation into residual stresses inherited during manufacturing of carbon-epoxy composites with delamination. The presentation is prepared by a group of researchers from Lomonosov Moscow State University and Skolkovo Institute of Science and Technology. The research was supported by the Russian Foundation for Basic Research, grant number 1831-20026. Last decades, an increased attention has been paid to the deep understanding of the processes caused by the residual stress in laminated composites, specifically shape distortion and possible damage of the product at the stage of manufacturing. The presence of residual stresses in the composite material affect the occurrence of such defects as delamination, warping, as well as the appearance of microcracks in the matrix of the material, which has a significant impact on the static and fatigue strength of the final product made of composite material. In the article, the effect of residual stress induced by manufacturing on strength on free edge of carbon-epoxy composite with 0.90 layup was shown that during modeling, the nature of fracture for a carbon-epoxy composite sample is significantly different when taking into account the influence of technological stresses in the composite. In particular, a certain type of crack, namely in the longitudinal direction along the application of the load, is realized only in models where residual stress are taken into account. The maximum stress obtained during the simulation for samples AS4 8552 of hexyl after polymerization is close to ultimate and can't be ignored in the subsequent strength analysis. There is an assumption that residual stresses near the free edge have a significant effect on the further propagation and growth of cracks. Even though the capabilities of process modeling technique have been improved over the past decades, the occurrence of localized manufacturing defects and residual stress distribution remains challenging to predict at the design stage due to insufficient development of the theoretical base, large number of input parameters, and lack of reliable scalable methodics. As a result, the manufacturing process of large composite structures still requires substantial investments in empirical optimization. In this way, an attempt has been made to fully evaluate the nature of the stress field and possible crack growth near the free edge over the time. It is an essential issue in the evaluation of composite structures for durability and damage tolerance. In this work, we consider the change of the distribution of the residual stress field caused by a manufacturing process in the specimen with the initial delamination defect, crack, due to appearance of the free edge cut. Different lengths of initial crack have been analyzed with well-known composite material AS4 8552 of hexyl. The current research consists of four main steps. On the first step, the modeling technique for prediction of stress-strain distribution at the composite structure caused by manufacturing process was developed and implemented in commercial finite element software Abacus. On the second step, values of residual stresses and G1 and G2 were determined in the composite sample of 3 and 12 millimeters of thickness, about 3.12 millimeters, and with 0.90 layup during the polymerization process, with initial crack of length 0.5, 1, 2, and 6 millimeters. On the third step, the sample with the initial crack of different length were virtually cut into two parts. The change of stress and G1 and G2 values were determined after ideal cutout and compared with ultimate. One of the key processes during manufacturing of composite part, and at the same time a bottleneck, is the polymerization of resin that takes place inside the die. At least three kinds of constitutive laws, elastic and pseudoelastic, cure-hardened instantaneous linear elastic, and viscoelastic law are currently used to predict curing process-induced residual stress for the thermoset polymer composites. To describe the behavior of the carbon-epoxy composite, in particular the behavior of resin during solidification, the child model was used in view much more efficient numerical implementation and shorter computation time. The driving equations are presented on the current slide. The Q degree rate of change depends on temperature and on the attained degree of Q and can be expressed by the kinetic equation 1. For a thermoset resin, glass transaction temperature Tg is related to a degree of Q and can be found by the Di-Benedetto equation, where Tg is 0 and Tg infinity glass transaction temperatures for the uncured and fully cured resin respectively. Lambda is material constant determined experimentally. Alpha is a degree of Q which takes values in the range from 0 to 1, uncured and fully cured resin. Mechanical properties of resin changes during solidification. It was considered that the Poisson's ratio of resin remains constant, while Young's modulus changes depending on temperature and degree of cure. Young's modulus was calculated by using Child, so the cure-hardened instantaneous linear elastic model, which presents equation 5. The two materials were used in model composite AS48552. It's material 1 for layers with orientation 0 and material 2 for layers with orientation 90. The polymerization material model was verified on the example of the warping of a plate. Figures show the development of the degree of cure, the glass transaction temperature, Young's modulus, and volumetric stress of resin obtained by modeling in Abacus. Difference between the curvature of the sample obtained from the finite element experiment and natural experiment is less than 3%. The developed model shows a good match with literature sources and can be reliably used for simulation of polymerization of the composite. On the current slide, the sample for modeling and taken assumptions are presented. The model was considered in the 2D plane strain formulation due to layer symmetry. In the present work, it was decided to exclude the mold from the analysis as it is insignificant for such sample. Sample considered free to move during all calculation steps. The cutout assumed to be ideal. The finite element model is shown on the slide number 8. Considering the layer symmetry, the model was analyzed in 2D plane strain formulation. The finite element model is constructed in such a way that the most elements have a rectangular shape and retain the shape during the mesh sensitivity analysis, changing only the dimensions of elements. The model is built up using both 3-node linear displacement and temperature and 4-node bilinear displacement and temperature reduced integration with enhanced hourglass control elements. The mesh near the free edge zone, the zone of cut, is more detailed in order to see the emerging effects in this area. The finite element model with local 1, 2, 3 and global XYZ coordinate system is presented on the current slide. Since the singularity expected at the delamination front, the fine mesh is done only in this zone and large elements used in the vicinity. Each lamina was presented by 8 elements per layer. The initial crack was placed between 0 and 90 ply. The cut process was realized by a special modeling technique by deactivating interaction between two parts after cure cycle simulation using an additional step of the analysis. The distribution of the local strain energy release rate along the delamination front is obtained via using seam crack technique applied to 2D finite element models of straight delaminations embedded in multi-layered composite. The use of commonly used virtual closure crack technique and extended finite element method were not applied in mind the limited use of methods during coupled temperature displacement analysis that actually we have in our case. The crack 0.5, 1, 2 and 6 millimeters long was placed between 0 and 90 layer. For each length of crack were calculated fracture criteria F1 and F2 according to the formulas 1 and 2 during cure of sample and after cut. The results of the finite element modeling, the distribution of residual stresses for the cured sample with the initial crack of 6 mm in length before and after the cut are presented on the current slide. When modeling the cutout, the effect of the concentration of maximum stress in the local zone of the free edge region arises. It was shown that the absolute maximum stress in the longitudinal direction is mainly concentrated in a small region at the free edge and is close to the ultimate straits of the composite material. It should be noted that the stress in the longitudinal direction is also close to the ultimate value after the mechanical cut and is in a small area at the crack tip. Thus, there is a possibility of formation of microcracks in sample during manufacturing or at low load, which confirms the conjecture about the reduction of mechanical performance, especially for matrix-dominated properties by residual stresses. As the next step of the analysis, the history of energy release rates under mode 1, 2, so G1 and G2 were analyzed over the time during process of polymerization and free edge cut appearance using seam crack technique. A slight increase in G1 and G2 values at the crack tip during the polymerization and the multiple excess of these values after the mechanical cut is shown in the figures 16 to 19 for different crack lengths. It should be noted that the length of the initial defect in the sample does not significantly and not quite explicitly affect the energy release rate G1 and G2, with the exception of the energy release rate in mode 1 during the manufacturing process. To assess the possible further growth of cracks, we analyzed the changes in fracture criteria F1 and F2 over the time for a specimen with a crack of 6 mm. The results are provided on figures 20 and 21. Values of the crack energy release rates are given for reference in the table based on the experiments described in the literature. It's important that the absolute value of the fracture criteria is much less than 1, which indicates the absence of the additional crack growth. Real composite structures can work under the cyclical loads. Under cycle loading, the limiting critical energy release rates tend to decrease with the increasing number of cycles. On the current slide, the change in the normalized fracture energy Gmax, depending on the number of cycles obtained during the experimental study, is shown for the material AS48552 of Hexel. The fatigue limit obtained for 3 million load cycles is 50% of the static critical energy for material AS48552. With the subsequent increase in the numbers of cycles, there is a possibility of a further decrease in the critical energy value. That is, the limit values of the fracture toughness during fatigue loading is typically orders of magnitude higher than the values realized in the sample by the residual stress. Thus, the fatigue characteristics of the carbon-epoxy composite will not change due to the presence of the initial stratification defects. To sum up, in the present study, the effective presence of residual stresses inherited during manufacturing and delamination defect in carbon-epoxy composite specimen is investigated. Based on simulation result, it can be concluded that the maximum stresses after cut in the sample are close to the ultimate and concentrated in a small area near free edge. There is a possibility of occurrence of microcracks in the sample during the manufacturing process as well as during a relatively small loading. A slight increase in G1 and G2 values at the crack tip during the polymerization and the multiple excesses of these values after a mechanical cut is shown. The growth of fracture toughness values during the manufacturing process and during cutout is sufficiently small as compared with the static parameters that favors the absence of additional growth of defects. The presence of relatively small defects in the sample or their occurrence during the manufacturing process will not introduce substantial changes in fatigue strength values. Obtained by modeling values for stress components are essential and cannot be ignored in subsequent structural analysis. The results of the study can be applied for prediction of residual stresses in composite structure by means of simulation and further understanding in the nature of fracture of composites. Thank you for your attention.